Well, hello friends. I'm going to give you the solutions of the two problems we didn't finish in this week's tutorial. The first one is problem 64, and we're asked to show that the set of polynomials, or four polynomials like so, cubic polynomials, which we need to establish, form a basis for the space of cubic polynomials. Well, there's four of them, so and the space of cubic polynomials is four-dimensional because there are four different coefficients, or four coefficients of the different powers of x. So, these polynomials will form a basis for the space of cubic polynomials if no non-trivial values of the parameters a, b, and c here can be found such that the linear combination a times the first polynomial plus b times the second and so on is the zero polynomial. Well, we can establish these parameters using that, and we now want to well, the condition for this polynomial to be the zero polynomial is that the coefficients of x to the power 0, 1, 2, and 3 need all to be 0. So we can calculate those coefficients by this, and we can see that they're all linear expressions in the four parameters. And we can so they're in other words, they're a set of or the left-hand sides of a set of linear equations for the four parameters, and we can dig out the coefficient matrix of that by looking at the coefficient of the jth parameter in the ith equation and running over the equations and parameters, and that will give us the coefficient matrix, which we can view as a matrix using this. So, well, the polynomials will form a basis if this matrix is non-singular, because if it's non-singular, then the only solution of the equations is the trivial one, and that will be the case if its determinant is non-zero. Well, the determinant can be computed by reduction to row echelon form. So let's do that. So we leave the first two rows as they are, and we add the second row to the third, the first row to the third, and subtract the first row from the fourth. And we can do that using this. And view it as a matrix using this. And we see that indeed we've got zeros all down the first column, or under the diagonal element. Well, now we want to do the row reduction on the second column, and we can see we've already got a 0 here, so we don't have to do anything with that. So we just need to subtract twice the second row from the third. So we can do that using this, and check that it's all good using this. Well, now we're finished, because this is now in row echelon form, and we can work out its determinant by multiplying the diagonal rows. So that's 1 times 1 times -1 times 1, which is -1, which is not 0, and therefore the matrix is non-singular, and therefore the four polynomials form a basis for the space of cubic polynomials. Okay, well, the second problem we didn't get around to solving was problem 11 in chapter 7, and that problem asks us for any function in problem 2, which is a linear map, to find a matrix A such that T of x, the image of x under the transformation, or under the mapping, is A times x for x in the domain, and using the results of the matrix representation theorem in section 7.2. We'll use as our example problem 2b, where T is the mapping from R4 to R3 given by this, where X is this four-dimensional vector here. And we can see that each entry of T of X is a linear combination of these four variables. So we establish this vector X, and we can visualize it as a column matrix using this, and then we can construct a matrix whose T of X, whose rows are the elements of T of X, using that. And we can view that as a matrix using this. Well, there are two methods given in that theorem for finding the elements of the matrix A. And one is to evaluate the map T of X when X is each, not one, is each of the four coordinate vectors here. So let's do that. So we can do that by taking our expression for T of X and replacing x1 by 1 and all the other x's by zeros, and then expressing it in matrix form, and that should give the first column of the matrix A. And we can do that for the second column, so we set x2 equal to 1 and all the other x's equal to 0, and that gives us the second column, and I think we've grasped it now. The third column is generated by this, and the fourth column by this. Now, the second method is more direct and can be done by finding the coefficient of the jth element of the vector x in the ith member or element of T of X. And we can use this, our tool from before, so we look at the coefficient of the jth element of x in the ith row of T of X, and we do that for all the rows or all the elements of T of X and X, and that gives us a matrix which we can view using this. And if we look, we can see the first row is this, -2, 6, -2, and if we go up here we can see that that's the same as this. So either method can be used.